Right, so we are continuing the calculations for ethanol, and we're now up to volume of carbon dioxide produced per kilogram. So once again, per kilogram means we're working with 1 kilogram of ethanol. And the carbon dioxide is being measured at SLC. So we change our ethanol, well, we use the same values that we had for the previous calculation. So we know we've got 21.7 mole. Substitute that in. This time it's the ratio of ethanol to carbon dioxide, 1 to 2. And so it's 21 to 21.7 to 21.7 times 2, 43.4 mole of carbon dioxide. And we want to know the volume at SLC, so we just multiply those moles by the molar volume, Vm, which is that one there. And that gives us 1,076 litres, or 1.08 by 10 to the 3 litres, once again for sig fig purposes. Next one is the volume of CO2 at SLC produced per megajoule of energy. So this time the megajoule of energy is the known, and it's 1. So 1 megajoule of energy. The unknown is what volume of CO2 at SLC. So we pop the energy in, energy to CO2 ratio, so it's 1235 to 2. Notice we don't worry about that negative because that's just in the equation as a code telling us that this is an exothermic reaction. So 1235 to 2, and we're not interested in 1235 kilojoules, we're interested in 1,000 kilojoules because a megajoule is 1,000 kilojoules. So look for your energy conversions. Keep an eye out for those as well. So now we're going to divide by the 1235 and multiply by 2 to get our mole of CO2. So divide by the coefficient of the known, multiply by the coefficient of the unknown. And I'm sorry if this is sounding repetitive, but I'm hoping that by the time we get through all of this, everyone will be very good at doing their stoichiometry. So we are converting our volume to, we are converting our mole to volume at SLC, hence multiplying by 24.8, and it comes out as a very neat 40.2 litres of carbon dioxide per megajoule. I think this is the last one, the total greenhouse gases. Now this time we want carbon dioxide and water. Now this time notice we're assuming that the water is a gas. Now I just want to go back. No, I'm not going to go back. But in this equation, we've just been assuming that water was produced as a gas. Now, I would hope that that number is different to the normal heat of combustion of ethanol. But let's not worry too much about that. In this sort of circumstance, if they really wanted you to be talking about water as a gas, they'd give you the right heat of combustion. Because usually we would be talking about water at this point as a liquid, because we would be assuming that water was produced under standard conditions. So don't worry about that. Sorry if I've confused you by pointing it out, but I did need to make you aware. So it's per megajoule of energy. So our known is 1 megajoule of energy. The unknown is the total. So it's the total of the CO2 and the H2O, and it's at 500 Kelvin and 1 atmosphere, which is 101.3 kilopascals. So we go ahead. Our total from the equation has to be the total of the two. So they're added together, the 2 mole of CO2 and the 3 mole of H2O. So we take our 1,000 kilojoules, we divide by the 1235, we multiply by 5 because we've added the 2 together, we get 4.05 mole. That then goes in to our PV equals nRT equation, where the temperature is already given to us as 500. The pressure, remember, has to be in kilopascals, so it's 101.3, and that gives us 166 litres total greenhouse gases. So when we calculate, when we compare these two, so in the textbook, the calculations that I just did are not done, but the values are here in table 3.5.1. And so what you're finding is that the energy content of ethanol is much lower than that of octane. The volume of CO2 per kilogram of ethanol is lower. So if you were just looking at volume of CO2, you might say, oh, well, ethanol's a wonderful fuel. It's wonderful. It gives out so much less carbon dioxide. But then when you look at the volume of CO2 per megajoule of energy, ethanol is now higher. Now, it's not hugely higher. Personally, I don't know that that's the biggest problem in the world. So we don't make a lot more CO2 per megajoule of energy. But then when you add in the other greenhouse gas, the numbers are starting to look a little different. So we've got quite a lot more greenhouse gas for ethanol than we did for octane. So, yeah, it's all very well to pop a bit of ethanol in your E10 fuel, but we don't want maybe to have a greater percentage than 10%. Right, so you can now do all of these calculations for butane. You start off by writing out the balanced equation, do the energy per kilogram, the volume of CO2 per kilogram, the volume per megajoule of energy, and the total greenhouse gases under the same conditions. So you can do all those calculations for butane, follow the previous slides, or try and do it off your own bat and then check the steps against the previous slides. I think what I might do is just, I'll summarize them at the, I will stop this as a short video. I'll summarize them at the start of the next video and then we'll finish this all off.